This is your question and answer session for week 3. We might end up having another Q&A, but we do have a quiz tomorrow, so that'll be quiz 3, and it will be over chapter 5. Hopefully you can watch the Zoom video and make models or make sure you get your priorities. Okay, so some of the questions we had were on the exam 2, some of the multiple choice questions, and I went through and looked at the ones that were most frequently missed. There's about 6 of them, and I'm going to kind of just go through this so you can learn how to think and solve these problems so you can get the right answers next time. The other reason is when you take your final exam in Organic 2, it will also cover the exam materials from Organic 1. Because this is such a short, condensed summer with 12 weeks, we're not going to have a cumulative exam in Organic 1, but we will in Organic 2. Okay, and then we're going to finish up with some of the POGIL exercises and just a little review for your quiz tomorrow. Okay, so this question asks, which proton has the lowest pKa value? So hopefully from this, you know that the lowest pKa value is your strongest acid. And so we can look at each one of this. This is a carboxylic acid. And this is where knowing your functional groups is helpful. Carboxylic acids have pKa values between 4 and 5. And if we were in class face-to-face, I would have you memorize these. Okay, this is a phenol. So it's an aromatic alcohol. Okay, so that pKa is about 10. This is an aldehyde proton. Okay, this is not acidic, and I'm guessing a lot of people might have been fooled by this, but let's look at the conjugate acid that gets formed if you were to make this. All right, so if you did resonance with this structure, you would have carbon has 4 bonds, that's 5. Fine, but how many electrons does this give oxygen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. This is an octet violation. This is not an acidic proton, okay? You can't even find a pKa value on it. And then this pKa value is on an sp carbon, hydrogen. That's called an alkyne. And if you look that up, you'll find pKa values of 25. So if you go by that reasoning, you can see that Hb is your most acidic proton. All right, so here's a question. What hybridized orbitals overlap to make the bond indicated in the arrow? So you have this compound. You need to put in your lone pairs, folks. This is still problem solving, okay? You don't want to just look at these compounds and just go from there. You need to recognize that this can form a resonance structure. And if it forms a resonance structure, then those pi electrons must be sp2. So now you can look at the things. So you have on nitrogen, you have 1, 2, 3. So that's nitrogen is going to be sp2 because you can add 2 plus 1, the superscripts. Okay, you look at carbon here. Carbon has 1, 2, 3. So carbon is an sp2. So it's a carbon sp2, nitrogen sp2 overlap. Okay, so this question, which represents the most stable conformation for 1 isopropyl 2 bromo cyclohexane? So what you want to do is you want to draw your chair conformation. And we can make this 1, and so I'm just going to put make sure that this is equatorial. If I put it somewhere else, I could do equatorial out, but I just need to make sure that's equatorial. So that's going to be, that's equatorial down is drawn. And then 2, we have an axial. I'm going to put a hydrogen there, and I want to put a bromine there. Okay, so this is equatorial up. What does that look like? That looks like this if you were doing a 2-dimensional. You can see here, this problem here is a 1, 3. Okay, so X out things like that. That's not going to work. Okay, here, this puts them as axial, and this is equatorial. Okay, this one's equatorial, and this one's equatorial. So this is your better choice. That's your correct answer. Okay, which of the following statements is correct regarding the following resonance structures? Okay, once again, when we're working resonance structures, you want to go ahead and put in your lone pairs, and then you want to draw your electron flow arrows. As you can see, we have these here. This is overall neutral, because there might be some that's wrong here. This is neutral. Look at there, okay? This, folks, is an sp3 carbon. It's an sp3 carbon. Okay, so this can't happen. Okay, so this is, so it says compound 3 is incorrect. Okay, so that's correct, that's true. Compound 1 is the major contributor. Okay, so compound 1 between 1 and 2 is the major contributor. Here, compound 1 is the major contributor. Okay, that's correct because of no charges. Compound 3 is the least major contributor because the charge is on the carbon. No, compound 3 is not a resonance structure. It's not a contributor. Okay, so compound 1 is the major contributor. Okay, we agree with that because of no charges. Compound 2 and 3 are both equally minor. No, 3 is not a contributor. Compound 1 is the major contributor, okay. Compound 2 and 3 are not correct resonance structures. What compound 2 is correct resonance structure? So your best answer is the first one. All right, which of the following bases would result in equilibrium towards the products if you placed in a reaction flask with, now students, you need to draw Lewis structures when you're solving these problems. Don't just go straight without doing that. Okay, so there's a correct Lewis structure, and so would be towards the product. Equilibrium would be towards the product. Okay, well, if you wanted to do sodium hydroxide, you could try this one, and this one here is an acid, CH3. This is acetic acid, so that's not even a base. So once again, we can throw that out. Water is not as strong as sodium hydroxide, so let's just see what sodium hydroxide would do. These electrons here would deprotonate, and then you would get your compound here, and you would get water. So if you want to, we can make this blue here. Okay, so this is your conjugate acid, so we got to do the pKa of that is 15.7. We say our acid over here is pKa of 25, so we're comparing 25 with 15. Okay, so that's going to be towards the starting material, so the reactants. Okay, so it can't be sodium hydroxide. So let's draw out the methyl grignard is what it's called. Okay, so now we add CH3, magnesium bromide. Okay, so magnesium gets a plus charge. Now we can basically take this and make this a negative carbon. And this is your acid here. We've already said this pKa is 25. And so those electrons, they're going to go and take that acid. And then you draw your product over here. That's your conjugate base, and then you're going to get this carbon, it's going to pick up this hydrogen here. Okay, so this is your conjugate acid. What's the pKa? That's about 50. Okay, now what happens in magnesium bromide is just going to hang out here because it's a positive. You got a metal there. So you're comparing 50 with 25. So that goes straight to the products. So which of the following bases would result in the equilibrium being towards the products? So there you go. All right, so this problem here, which of the following compounds represent a stereoisomer for the compound below? All right, so this is, can you convert this into a two-dimensional structure? So here we have methyl coming at us, and now this is on 1, 2, 3. On the 1, 2, 3 carbon, we have, and I draw these, folks. Draw in your hydrogens, okay? So this is hydrogen going up, so that means that the carbon-carbon double bond substituent is going down. Okay. You see that that's going up. So these are the following represents a stereoisomer. Okay, so stereoisomer. So this represents the same. This is the same compound. This is, what's the carbon? We have C6, 7, 8, 9. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so there's our molecular formula. You would see that this has the same. This is C6, 7, 8. How many hydrogens? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, these are different compounds. Okay, these are totally different compounds. This, you see, this is a totally different compound. So here, this is trans, and this is cis. So this would be a stereoisomer. A lot of times people just are not taking the time to read the question. I would recommend, you do have 2 hours. That is plenty of time to take this, folks. 25 multiple choice questions given to you in a face-to-face class. I give you about, that's 30 to 40 minutes. Okay, that's 30 or 40 minutes. And then you have the open response. These exams that I have written are a 1 hour exam. And I do have students that get them done in 30 or 40 minutes. So, and that's without notes or looking up anything. That's from their own memorization. And people typically get in the about 70th percentile. So you have 2 hours to work the these multiple choice questions, and then the open response you essentially have most of the day. So you have access to your notes. Read the questions, draw out the problems, get some scratch sheets of paper, make sure you're reading stereoisomer, okay? Get that out of the computer. All right, which of the following Newman projections best represent the conformation of the compound displayed? All right, so do you see that this is eclipsed? So here's the methyl and the hydrogen, and they're eclipsed. If we look at this hydrogen and this isopropyl, they're eclipsed. The bromine and the fluorine are eclipsed. So I'm looking for eclipsed structures. This is staggered. This is staggered. Okay, so this is eclipsed, and this is eclipsed. So I'm going to pick between these two. I see I have a methyl. So we have the methyl and the hydrogen. Keep in mind this is your back carbon. And then we have the hydrogen here with the isopropyl. But you see the problem? What's the problem here? We have the fluorine here. Well, this is correct. The fluorine with the bromine. Okay, so that's your correct answer. Let's look at here and see what we have. We have the methyl and the hydrogen, and then we have a hydrogen and the isopropyl, and then we have the bromine is on the front here, whereas the fluorine's on the front. You see the fluorine's on the front, so these have been switched. How do you catch that? You slow down. You draw each one of these out. Okay, you work each one of these like they're open response, and you will get the correct answer. All right, so now for your POGIL. So I have some POGIL activities here on the next two slides, and this is POGIL 7 and 8. Looking at your list of your 5 multiple choice questions on quiz 3, you're going to have to star your stereogenic centers. So you're going to have to be able to find the stereogenic centers. You're going to have to define the relationship. So we're going to work an example problem for those. You're going to have to assign configuration. So we're going to do that. Configuration is R and S. And then convert Fisher projections and do Fisher projections. Okay, so these are some of your POGIL exercises. You see here that you might want to think that this is an asymmetric carbon. It's got a methyl group, which is different. It's got an OH group. But the problem is this CH2, CH2, and then you go here to CH2, CH2, and then you meet. Okay, so that means it does have a plane of symmetry. So plane of symmetry, and that makes it achiral, achiral, and no asymmetric carbon. Okay, so you come here to the next compound, and we see that this is different. That's different. Hydrogen's different. OH is different. And the CH3 is different. And we have to assign priority. So this is definitely chiral. And we need to assign some priorities. So priority number 1 would be oxygen. Okay, so it has a atomic number of like 8. Hydrogen's going to be 4. And then you have this is going to be 3 because it's carbon with 1 hydrogen, so that's bonded to 2 carbons. So if you did your carbon tree, you would see that that is 3, and this is carbon bonded to only 1, or itself, not really bonded to any carbon. So there's 2. All right, so now you want to be able to put your hydrogen in back, and this is where I would want to make my models, and I would move it back. But and you can see if you do that, then you've got the OH, and it's going from 1, 2, 3. I'm going to go and actually get models real quick and just check this. If you don't have models, you can try to get some toothpicks or something and just try to make sure you can do with the hydrogen in the back. I try to make sure hydrogen or your lowest on your assessments are not on the plane, because sometimes it can be tricky. You see how what I mean by on the plane is it says the straight lines. So here I will, so see these straight lines here? That's on the plane. And so I am making a model right now with, and I'm just putting the black and I'm putting a red for, so I just got 1 black carbon, and then I'm going to do the acetylene, I'll just make it like green, and then I'll make the other one yellow, blue. So I have 4 different colors, and actually I'm going to keep them with the same color. So I'm going to put my yellow is my 3 priority. So you could just do these with colors. I'm going to make my yellow my 3 priority. I'm going to make my blue my 1 priority. I'm going to make my green, and then I'm going to make my red my 2 priority. So now I'm going to put that in back. And so when I put my hydrogen in back, but first I'm going to make sure I have it drawn correctly. Okay, yeah. So now I see that I go from, I have my OH here, and then it goes to the 3, and then it goes, so if I could draw a picture of what mine looks like right now when I put it in back, I have, um, so when I rotate this in back, this is what it looks like. I have I have my blue, and I have my red up here. And so what you don't see is the hydrogen in back. Okay, and so now if I do my priorities, which this is 3, and this is 1, and this is 2, I do 1, 2, 3, and you see that that is S. Okay, so that stereocenter is S. So then the next one is this one right here, and you can see that there are 2 stereocenters. So let's go ahead and just star those. And we're going to try to assign R and S. Let's first see that there's 2 stereocenters. What you don't see here is the hydrogen in back, so go ahead and draw that in. And that's going to be a 4, and the oxygen is going to be a 1. And then you see that if you go here, this is different than the other one. One's a methylene and the other one's a carbon bonded to 3 carbons. So that's going to be 3 or 2. That'll be 2. This will be 2, and then this will be 3. And so here you go 1, 2, 3. So we see that that is R. Now, I'm going to make sure that it is. Okay, so I'm going to put green in back. I'm going to make that hydrogen green. I'm going to keep with my same color. I'm going to make my 2 blue. Okay, so this is blue. And I'm going to make my 3 red, yellow, and then I'm going to make 1. So the way I have my molecule drawn, I have 1, 2, 3, which is R. Okay, so let's look at the other. So this is R. That stereocenter is R. And what about the other? Well, we have CH3, we have this carbon, and we need to draw in our hydrogen. So draw in your hydrogen, that's going to be 4. Let's make that green. So this is going to be number 4. Number 1, we're going to make blue. So number 1 would be carbon oxygen. This is going to be number 1. Okay. Number 2 is going to be, we'll make that red. This is going to be number 2. And number 3, we're going to make that yellow. Make that 3. So here we have 1, 2, 3. And with hydrogen in the back, that's S. So we have an R and we have an S. All right. Rings are a little bit harder, but okay, so let's look at this compound. If I'm signing these, that means they're chiral. So that's chiral. Is this molecule chiral, achiral? Okay, hopefully you can see that that's chiral because you have 1 stereocenter. Do you see that you have 1 stereocenter? So this is your stereocenter. You have 4 different groups. We'll make hydrogen green because it's in the back. That's 4. Number 4. We'll make number 1 red. Number 1's going to be this carbon right here. we'll make number 2 carbon. Oh, well, sorry, let's do 1 carbon blue. We'll do 2 carbon. So this is 1. This is priority number 2. Do you see how I'm signing the priorities? And then number 3. So let's look how I sign the priority. 4 has an atomic number of 1. We've got carbon, 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 but this carbon, the blue carbon, is connected to a carbon with carbon double bond. So if you did your tree there, that you would see this is carbon, 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 and then that carbon would be back to that carbon. So that's going to be 1. With hydrogen back, you can just do 1, 2, 3, and that will be clockwise, which is R. If I draw this here with my colors, and I can just do that, I'm just switching my colors here. Hydrogen back, we have blue. If I do the 1, 2, 3, yes, it's definitely R. Okay, so that is the only stereocenter. Do you see that the other ones are CH2s, which are not going to be asymmetric carbons, and then a carbon-carbon double bond is a carbon bonded to itself. So that's not going to be. Okay, what about this compound? Okay, so hydrogen is number 4, but it's coming at you, isn't it? Okay, what's the next largest atomic number? We'll make that one blue. It's the chlorine. That's right. So that'll be number 1. And then fluorine would be the next atom. So that's going to be, we're going to make that red. That's going to be number 2. And then number 3 is going to be yellow. And so we'll make that 3. Now we want to connect 1, 2, 3, 1, 2, 3, and so that's R, but we have to do a switcheroo because hydrogen's at us. So R will switch to S. So this stereocenter is S, and this would be a chiral molecule. And I have my carbon here with the different colors, and so if I just switch them here, so I put make it look like my drawing. Now I can take the hydrogen and back, and I can go 1, 2, 3, and yes, that is S. Because when I actually physically put this in back and I connect 1, 2, 3, it would definitely be S, counterclockwise. Okay, this last one here, hopefully you can see that there is the symmetry. Okay, and so this would be a chiral, and this is called a meso compound. And a meso compound means that there are stereocenters, so we have 2 asymmetric carbons, but because the compound has a plane of symmetry, it's achiral. Now, one of your questions on your quiz tomorrow is going to be about rotating plane polarized light. This will not rotate plane polarized light. Now, why was that? It's because it's achiral. Achiral molecules do not rotate plane polarized light. Okay. We are going to do POGIL question C, and this is a Fisher projection, and we have to determine the relationship. So I'm just going to show you how I would do this. I would first start with my top compound. I would see that I would number them. So I would go 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Each carbon has, so this is an aldehyde, we have an OH, OH, OH. So I'd see that they have the same connectivity. So I would need to assign R and S's. How many stereo centers do we have? We have 3. So we're going to do 2, 3, and 4. We're going to do the same here. 2, 3, and 4. So we're going to fill in those blanks, and this is going to determine the relationship. Okay, so I'm going to go through here, and we're going to do green is the 4th priority. Let's keep with our little color coding. We're going to do blue is the number 1. We're going to do red is number 2. And then we do yellow is number 3. Okay, so I come here and I have an oxygen, a carbon, a hydrogen, carbon. So number 1 is going to be the oxygen. Number 2 priority is going to be the C double bond O. So if you didn't know what this looks like, it's an aldehyde, C double bond O. My last priority is going to be the hydrogen, and then this carbon oxygen will be 3, because this is carbon oxygen. This is carbon double oxygen. Okay, so that's why it gets a higher priority. So now we have, we're going to connect our 1 with our 2 with our 3. Okay, and so what is that? You'd say that, well, that's R, but because hydrogen is coming at you on these bow ties, it's a S. So I'm going to put S here, okay? And then we're going to go to the next one. Just do this, make it neat. All right. So now we're going to go to the next one. This is our next carbon, 3. And we're comparing, so hydrogen will be 4. And our number 1 is going to be the oxygen again. Our number 2 will be the carbon, oxygen, carbon double bonded oxygen, and then 3 will be this carbon oxygen. Okay, so we're going to connect 1, and then 2, and then 3. So we're going to connect 1, 2, 3, and that's going to be R, but the hydrogen is coming at you, so we have to switch it to the S. So we put the S there. Okay, now we got to go to the next one. Let's clean this up a little bit. You can erase with pencil and do it that way, but you're going to need to draw these out and take your time. All right, so now number 1 here will be this oxygen here. Number 2 is going to be this carbon chain, because it's got carbon oxygens. Number 3 will be this carbon CH3, and number 4 will be hydrogen. Now we connect our 1, 2, 3. We connect our 1, 2, 3, and that's turning it S, right? You're turning the steering wheel to the left, clockwise, but you see your hydrogen's on the wedge here, so S has to switch to R. So now we put R there. Okay, now we want to do this in this, it's called a perspective drawing. So this was a Fisher drawing, and this is a perspective. Okay, so let's do our assigned priorities. So 1 is going to be the oxygen again. The CHO will be 2. 3 will be this carbon, hydrogen. Now what is not drawn here? The hydrogen coming at you. Okay, so you're going to have to draw that in. Always draw it on the same side as the dash and wedge, okay? Otherwise you're going to probably get it wrong if you don't. All right, so now we're going to connect our 1, 2, 3. 1, 2, 3. What is that? That's R. But hydrogen is coming at us, so we have to switch it to the S. So 2 is going to be S. All right. Now we go to our next group, our next carbon here, and I'm going to erase it a little bit just to clean it up, and we're going to color code it. So our number 1 is going to be oxygen. Our number 2 will be this carbon oxygen, so that's going to be 2. Our number 3 will be this carbon oxygen, and then number 4 is going to have to come at us again, and that is going to be the hydrogen. We want to connect our 1, 2, 3, and this is what? Counterclockwise, so that's S, but hydrogen's coming at us, so we have to switch it to an R, so that's going to be R there. All right, and then let's do our last stereo center assignment. And what do we have here? We don't have hydrogen in there, so we can draw that in. What's nice is we get to draw it in the back, and you know that that means it gets to stay in back. We're going to go with the blue is our number 1, so that's going to be oxygen. Our number 2 then will be the carbon oxygen, so that's number 2 here. And then number 3 is going to be the CH3. So now when we connect these, we have 1, 2, 3, and that is R, and R is going to stay R because hydrogen's in back. So we have R, R, we got S, S, and then we have one that's different. So we have this one center that's different. So what does that make it? That makes the relationship for these as diastereomers. What would an enantiomer of this be? What would that enantiomer be? It'd be 2R, 3R, 4S. Okay. What would the enantiomer of this one be? 2R, 3S, 4S. So every one of these would have to be different if they were going to be enantiomers. But when just one thing's different, you have 3 stereocenters, these are diastereomers to one another. And those are stereoisomers. All right, well, I hope that you're getting comfortable with stereochemistry, and I hope that you log on and do your Sabling and you download your open response quiz 3 tomorrow and have everything submitted to me by 5 p.m. is the goal. If you have any issues, please send me an email.